All right, welcome back to another lecture on special relativity in Physics 3210 at the University of Windsor. I'm Dr. Hammond, and we're going to discuss the structure of spacetime. So we've already talked about Lorentz transformations. Now we want to talk a little bit about the structure of spacetime, Minkowski diagrams, and covariant and contravariant vectors. So now that we've recognized that we can't just think of space and time separately, but these Lorentz transformations actually affect both space and time, we'll actually lump these together into space-time. So for this, we use four vectors. So we have CT, X, Y, Z. These actually have all units of space. And we'll call this a four vector with X to the naught, x1, x2, and x3. And so x just means it's some position, and this upper index tells us where in this four vector that we are. So these Lorentz transformations now, using beta as v over c, that we get x bar, the zeroth component, is going to be gamma times the zeroth component of x minus beta times the first component of x. So if you remember, the zeroth component is ct, and the first component is x, and the first component and the second component x bar, so x bar 1 is gamma x1 minus beta x0, and then x2 bar is the same as x2, and x3 bar is the same as x3. So again, we can put this into a transformation matrix where we have x bar 0, 1, 2, and 3 is transformed by x 0, 1, 2, and 3 by the Lorentz transformation matrix that we saw previously. So this can also be written more compactly by the Einstein summation convention, which is that this is summing from the 0th index to the 3rd index through the Lorentz transformation over this x4 vector. And you can write this more compactly, just skipping this summation sign here, that this x vector transforms through the Lorentz transformation to give us x bar. And so you sum over the nus to give you mu's. All right. And that's what this compact notation means. It's just you're using this Lorentz transformation matrix. So now we get into some definitions. So you may not have heard of contravariant and covariant vectors before. Basically, it's now that we're dealing with four vectors. We have three that are dealing with spatial dimensions and one that's dealing with time, but of course it's time times the speed of light, so it's also a spatial dimension. And we'll be using the same convention as the textbook, which is, I believe, the Minkowski convention, which is that when we have x with this subscript mu, it's called a covariant vector, and it's a lower index means covariant, and x with the upper index mu is a contravariant vector, and so the upper index is contravariant. And the only difference between contravariant and covariant vectors is that when we have the lower index, it means we can transform from the covariant to the contravariant by just multiplying that first component by a negative sign. So that this would be negative CT, whereas this would be positive CT. And the reason for that is, we'll discuss that in the next bit here, is when we want to multiply these two vectors together, so we have this delta x with this mu index will be xa minus xb, and we multiply these two vectors together to give us this unit vector. And that gives us, this is how we would write a four vector dot product. So if you recall from a three vector dot product, what you get is x squared plus y squared plus z squared. But in this case, we also have CT, and so we have CT from the covariant vector, and we have minus CT by the contravariant vector, so the covariant times the contravariant gives us minus CT squared. And so in total, this gives us minus CT squared minus c squared times t squared plus d squared, where d squared is delta x squared plus delta y squared plus delta z squared. And this was your question for the daily assignment, was describing the differences between time-like, space-like, and light-like. And so this is a bit abstract written here, but basically if this vector or this four vector dot product, I should say, is less than 0, then we call this time-like. And so if this is less than there, that means that this is bigger than this. So that means that the time part is bigger than the spatial part. If this part is bigger than this, then that means that this 4 vector is greater than 0, and this is called space-like. And if it's exactly equal to 0, then this d squared is equal to minus, or is equal to ct squared. And that's what we had in the last lecture on when we're riding the wave of the front of a light pulse. So maybe this will help if I show you this figure. So using this Minkowski space-time diagram, we have space on the x-axis, and we have the speed of light times time on the y-axis. And this is kind of the convention of how to write it. If something happens anywhere in here, then you'll be able to see it. If something happens out here, it happens after this present time, because the speed of light can only go so fast. And so right along here, or right along here, this is right along this light-like cone. And so this is like riding the wave of like a light pulse. But what you're seeing right now, this is everything that you can see in the past, and then this is everything that's in your future. And anything that's in your past that's going slower than the speed of light will be approaching you and going away from you in time-like curve. But anything, so when in the previous case, we had this example of 2 people talking. So somebody was standing over here and you're standing over here. You're obviously standing next to each other space-like. You're separated in space. And then this person says something, right? So they say something. And so that communication, it goes obviously time-like. So that's what's going on when we're talking about time-like, space-like, and light-like. And that's how that relates to these to this 4 vector dot product. All right, so hopefully that clarifies a little bit. I find the textbook gets a little confusing because it gets into some minute details about how you have simultaneity and things like that. And so that's kind of like a simplified understanding of what we mean when we're talking about that. We'll also talk, something that's really useful is using proper time. And so this is, as Einstein would call it, Eigenzeit. And so that's when you hear eigenvalues, things like that, what they mean is proper or own. And so Eigenzeit means like its own time or its proper time. So we use this Lorentz transformation, this 1 minus u squared over c squared to the 1/2 to give us this proper time. And so proper time is invariant because the time that the object says it is independent of its velocity. So it's the time that you have in that object, okay? And so we define this, we kind of make this weird abstract definition of proper velocity, which would be the distance that the object travels as observed by a stationary observer divided by its proper time. So the example that they give in the textbook is that you have a plane flying overhead of you. You see how far that plane flies, but the pilot in that plane tells you how long it takes to travel that distance, and that's what this proper velocity is. So it's kind of a strange way of defining it. It's not the Earth, the person who's stationary measuring both the space and the time, and it's not the person in the object that's flying by, their distance and time, but instead it's the combination of the two. So it's the length of the stationary observer divided by the time in the object that's moving by. So as I make a note here that the ordinary velocity would be that length that it travels divided by the stationary time. So obviously to translate from time to the proper time, we have this gamma factor, so we'll use this proper velocity eta. This is the notation that we have in the textbook. So eta, this proper velocity, is equal to gamma times this velocity, this ordinary velocity. And so then that means that we can define this 4 vector as this eta 4 vector component is going to be the derivative, is going to be defined as each component of this 4 vector divided by its proper time, or the difference in this proper time. So if we notice, then we think about this first, or the 0th component, so eta 0 is going to be dx0 by the derivative of the proper time, and that's going to give us c times dt by d tau, and so that's c gamma. All right, where the first component of eta, so the spatial component of eta, is dx 1 divided by d tau, is going to be gamma ux, so the velocity in the x direction. And so what that means is that spatially we have the proper velocity is equal to gamma times this ordinary velocity, and the 0th component is the proper velocity in the time component is going to be c times gamma. Okay, so I have an example here that you can see in the notes. Basically, it's some example that I think is in the textbook to convert from the proper time to the ordinary velocity, and then I go back from the ordinary velocity to the how it's defined based on the proper velocity. And this is also an example of how to use this in terms of this this hyperbolic tan function that we had used as also kind of a way of thinking about these Lorentz transformations as their hyperbolic rotations in this space-time. But the thing that I want to discuss is the dot product, the 4 vector dot product of this proper velocity. So I say find this 4 vector dot product, so eta, the contravariant times the covariant vectors of the proper velocity, and of course the contravariant times the covariant is the same as the covariant times the contravariant. And so we get that the 0th component times the negative of the 0th component plus the first component times the first component, second component times the second component, third component times the third component, just like a dot product. You don't have any cross products because they're all orthogonal vectors. So we get negative times the 0th component squared plus all the spatial stuff squared. So if you remember that we have this proper velocity, the x, y, and z components dotted with itself will just give us this eta squared. But we already calculated what those were previously, and so we get negative c gamma all squared plus u gamma all squared, and so we get negative gamma squared c squared minus u squared, but c squared minus u squared can be simplified as 1 minus u squared over c squared times c squared, and so that just cancels with gamma squared, and what we get out is minus c squared. And this is called invariant, and so what that means is this is just going to be equal to a constant, just like if we had some vector in 3-dimensional space, so a 3-dimensional vector in 3-dimensional space, we took its dot product, it wouldn't matter how we rotated our coordinates. So just like when we talked about 3-dimensional or 2-dimensional rotation of a rotation matrix, so we have this r length, and then we rotate our axes, it doesn't change the length of r, so it's invariant in this rotation. So in the exact same way, we have this minus the speed of light squared is invariant, and so that way, you know, it's nice because then it doesn't matter what our frame of reference is because this is invariant. I think I'll end here for these lectures because after this we start to get into relativistic mechanics because we'll be talking about energy and momenta and things like that. So we'll end off here for today's lecture, and then we'll get into relativistic mechanics in the next lecture.